Now coming to the special category of 8086 instruction, that is string instructions and machine or processor control instructions. So we'll discuss first the string instructions, and then we'll discuss in the later part of the presentation is the machine or processor control instructions. The instructions, the string instructions, we have movsb, that means move string byte, and this movsw, that means move string word. It basically moves the string byte from one segment to the other. So the one segment by default is data, and the other one is the register, the destination segment is the extra segment. So the byte is moved from the data segment to extra segment. And to calculate the address from which the byte is to be moved, we use data segment as a segment address, and SI, that means source index register, will provide you basically the offset address for the memory location from where the byte is to be moved. And similarly, extra segment data will provide you the segment register, will provide you the memory location of the extra segment address basically, and DI, that is destination index, will provide you the offset of the destination address for the location, exact location at which we want to move the byte. The similar instruction is used if it is 16 byte long, that means two consecutive bytes, that means we use movsw. This is similar to movsb, but the next byte is to be fetched from the next location in the data segment, and it will be moved into the next memory location of the extra segment. Next is compare. So compare string byte and compare string word. SB, that means it's 8-bit comparison. SW, that means it's a 16-bit comparison. And we'll compare the data from extra segment and a data segment. And after that comparison, there is no change in the data in any of the segments. The only thing that changes is the flag, because in compare command, in compare instruction, we only change the status of the flags. No data from anywhere is going to be changed other than the flag status. So CMP SB, that means we are comparing the bit 8 byte, basically 1 byte, 8 bit or 1 byte. And if CMP SW, that means we'll comparing the 16 bits or 2 bytes. So subtract the byte available at extra segment and DI combination from this data segment and source index register. So this is the, for example, this is the A, and this extra segment will provide you another byte, that is B. Then we'll calculate the difference, A minus B. A is the data segment byte and B is the extra segment byte. Similarly, if we compare the string word, then obviously A will be data segment plus data segment plus 1. That means data segment and the next byte from the data segment itself will give you a 16-bit word, and other word which we'll get is from the extra segment. So extra segment and extra segment plus 1, that will be the 16-bit, and these 16 bits are compared, and only change will occur is in the flags, not in the data. The bytes from which we are doing the comparison, they are unaffected, simply unaffected. Next is load string byte and load string word. Load string byte, that means if we are going to load 8-bit, that means we should use an 8-bit register, that is by default AL register. That means data segment, the byte from the data segment and SI, we'll move, or we'll load the byte available in data segment into the AL. It's an 8-bit register, so 8 bits are moved into AL. Similarly, load SW, that means data segment and 2 bytes from the data segment will be moved into 16-bit register, that is AX. Similarly, if we want to use the byte storage into the into the extra segment, then we use STOSB, store a string byte into AL and store a string byte into AX. Store a string word into AX. Because it's an 8-bit 1 byte, it is 16-bit 2 byte. So 2 byte means register is 16-bit and register is 8-bit. That means it is 8-bit register or 1 byte long. So as the destination is in the extra segment, that is why we'll use stosv command to store the data available in AL into the extra segment, because extra segment is destination. Similarly, if we want to store 2 bytes or 16 bits from AX, then it will be stored into the extra segment using the destination index register. Next is if we want to compare the string byte and string word. Now the thing is that we compare the string byte, that is done by subtracting the byte from the extra segment from a byte at AX. If we are going to compare the byte which is stored in AX, 16-bit data available in AX, and the 16-bit data available in extra segment, this AX is missing here. You can write it at AX. So AX data will be compared with this byte available in extra segment. Sorry, it is AL, basically 8-bit. So it's an AL register. The data available in AL will be compared with this ES. And obviously there is no change in the contents of the memory location or the register. The only change is in the flags. Similarly, if we want to compare the string byte using with the AX content, then this will be done using SCASW, and obviously the data available in memory or in register are simply unaffected. The only thing that changes is the flag, so only flags are changes. Now the three important commands are REP, REPE and REPNE. Now these REP is basically the decrement the content present in the count register, that is CX, and repeat the following string operations if CX is not equal to 0. So conditionally or unconditionally it can be used as a loop. So REP stands for repeat the following string operation. Whatever string operation we are using, we can repeat until this CX is not equal to 0. If it is equal to 0, that means it breaks and execute the next instruction. Otherwise it will go back to the to repeat the string operation. Similarly, REPE, that means we need to decrement the count available in CX because it's a default count, and we repeat the string operation if we check two conditions: if CX is not equal to 0, obviously, and since it is parity even, or repeat when equal or 0. So equal or 0, that means ZF has to be equals to 1. So we need to check these two conditions whether the conditions are true. If they both conditions are true, then only it will repeat the string operations. Otherwise it will go back, it will go and execute the next instruction. Similarly, REPNE, that means it is simply not equal or not 0. So repeat if not equal and repeat if not 0. That means it by default decrement the CX, the content available in CX, that is count basically, and repeat if this condition is same for all the three conditions, and in this case it checks the 0 flag equals to 1. So if 0 flag is 0 and CX is not equal to 0, we check both of the conditions and then we'll move to repeat the following string operations. Now next is a machine or processor control instructions. We have 5 machine or processor control instructions. That is halt, we have already studied. NOP, that means no operation. Lock, escape and wait. These 3 are different, so we'll discuss mainly these 3. That means the instruction that stops the execution and it places the processor in halt state. Next is a no operation. That means it does not do anything. It simply provides a delay. Next, lock instruction. It claims the hold on the use of bus of a processor. it activates the lock bar signal, external locking signal, and it places a prefix in front of instruction for which a lock is to be claimed. The lock is to be claimed for the following instructions like exchange, add, or add with carry, subtract with borrow, and subtract, XOR, not, negate, increment, and decrement instructions when they involve a memory operand other than the register operand. And if an instruction which is not mentioned here, the arithmetic and logical instruction other than these, then a lock prefix uh, will generate a trapped interrupt if this lock prefix is used with any of the instructions other than these instructions. Next is escape. It used to pass the instructions to a processor which is not 8086. It is basically with sharing like 8087 and 8088 and other processors. If it is sharing, then the escape ESC instruction executes. Instruction for a coprocessor represented by a 6-bit code embedded in escape instruction. So 6-bit code embedded in this escape instruction, and coprocessor which we are going to represent it along with the 8086. This will be happen by the 6-bit code. The coprocessor treats all normal 8086 instructions as no operation. So if co-processor has any operation of 8086, then it will simply treat it as a no operation by the 8087 processor, because 8086 and 8087 both are different processors. So when a coprocessor 8087 is associated with this 8086 microprocessor, then 8086 instructions will be considered as a no operation by the 8087. Next is wait. When the instruction is executed in 8086, 8086 check the status of the input pin, and if the input is high, it enters into the idle condition. That means it does not do any processing, and the 8086 will remain in its state until the input pin is made low by an interrupt signal received on the INTR or any non-maskable interrupt pins. Wait instruction does not affect flags. It is used to synchronize 8086 with external hardware such as 8087 coprocessor. So if we want to synchronize the data transfer between the processor and the coprocessor, that we can simply use the wait instruction, which synchronize 8086 processor with another processor or another coprocessor. Thank you.